is the second half of our session. This is the Planetary Science and Exploration Systems session, so welcome all. I will be introducing each speaker, and then Dr. Sharp will be giving the timing, so keep an eye on speakers. So today, first up, we have Olivia from the Northern Arizona University. Olivia here.
Yeah.
All right. If the mic is not in the right place, we can adjust.
Yeah. How are we going to change this?
Oh, slide pointer. Here it is.
Alright, so
That's it. One is a laser pointer and one advances the slides.
Alrighty. Alright. Hello, my name is Olivia Vester, and I am here today to present the work I completed under my mentor, Dr. Coyote Oshinobi. This project is entitled Building Computational Models to Understand the Interplay Between Climatic Factors, Air, Transportation, and Infectious Disease Dynamics. And it reflects just a portion of a larger research framework related to disease dynamics. Alright, so for some background, the West Nile virus is a mosquito-borne disease that affects horses, birds, and humans. And when contracted by humans, the development of the disease can happen in a few different ways. A majority of the people who contract West Nile virus do not experience any symptoms, but those who do often experience an illness similar to the common flu. However, according to the CDC, 1 in 150 individuals develop more severe cases that cause neuroinvasive infections like encephalitis and meningitis, which can lead to serious complications and even death. Because of these risks, it is important to study when and where they may be most prevalent. Since Arizona's Maricopa County is the largest contributor of cases in the nation since the virus entered the United States in the late 90s, it is a significant area of study for identifying risk. And this is just a graphic that shows that Maricopa County is in the top for cases in the United States. It is actually the top. So for some relevance, throughout the basis of this project, the basis of this project is centered around disease dynamics and targeting risk to humans, but a considerable factor in this data is climate. As we all know, Earth's climate is changing due to a larger number of reasons, and as a result of that, the Earth itself is changing. This visual reflects how mosquito dynamics and subsequently the West Nile virus dynamics are projected to change in the next 30 and 60 years. This is in the interest of NASA for their climate research, and these projected changes that show an increase in disease transmission from mosquitoes due to the changing climate. This is an informational data point that can contribute to further understanding of climate change. So as you can see, as the years progress, the mosquito population grows. And mosquitoes mostly inhabit warmer areas, so shows the climate changing in the warmer direction. So what's the main point? To help identify these risks to humans, we want to create models that account for climate, space, and time, because bird and mosquito dynamics are a factor of climate. Climate varies across space and time, so making a model at the county level can help target more precise predictions. To build these models, a new software system called Epimorph is to be used. Epimorph is a Python system within the broader project of epidemiological modeling resources of public health that can produce these mathematical models. The models are based on equations withdrawn from this visual that connects human, bird, and mosquito dynamics. From this chart, three main equations emerge that lay a basis for predictive data. Using the box and arrow plot, intrapopulation models can be created to make this data graphical. As for the data I'm presenting today, I'm using equations for birds and mosquitoes, and those are boxed in here. Key transitions here are susceptible to recovered birds and susceptible to infected mosquitoes. Okay. So as for the methods of this, in addition to the intrapopulation model that I mentioned on the previous slide, there are other components that come into play for these models to be functional in the epimorph system. The end goal for the modeling project is to get all three main components incorporated into the results. The components are the IPM, which is the intrapopulation model, a geo, and a movement model. The IPM lays a base for the data to be simulated. It contains the event cases represented by the box and arrow plot on the previous slide. The geo component is essentially code that incorporates location data and can also include significant factors like temperature and precipitation, which is the climate. And the movement model component adds in information about species travel and how the population in the area changes over a specific period of time. In the data I am displaying today, only the geo and IPM pieces are implemented because this is a step-by-step process and it has taken a lot of work to get just those pieces in place. So for this slide, it shows some simulated species abundance for 2014. So using the methods described on the previous slides, a number of simulations can be created that model different factors of the West Nile virus. There are dozens of graphical outputs, so the epimorph team has selected a few to discuss here as a display of these results. These particular graphs displayed on this slide are indicative of simulated data of the abundance of birds in Maricopa County during the year 2014 and the amount of infected mosquitoes per 1,000 for that same year. Since this disease is mosquito-borne, seeing the amount of infectious mosquitoes simulated within the county in a single year is necessary. The adjacent bird abundance data shows infectious bird counts simulated in the area within 2014 as well. This pattern shows how the bird population changes throughout the year and has its highest infection level in the late summer, which coincides with the warmer temperatures. So results and interpretations. So the prediction models created from this project are based on pre-existing data. So as you noticed, I was showing simulations for 2014, and that was so that we could verify that the simulation works with data that we already have. So we use that to compare how well the predictive modeling is doing. So to show these results comparatively, this is a graph showing the abundance of mosquitoes in one of the geoclusters, which is not quite the county, it's just an area within the state that's similar in structure. This graph shows between the years 2006 and 2014 and the complementary data from that time. So the orange line is the simulation and the blue line is the real data. And as you can see, the models are very similar and thus the predictive models appear to be successful. But the project is not done. So future work for this project, the next steps for this model include finishing up the human part of the model, which is this other red boxed in part. And it's complementing simulations which would produce those graphs and more. So that would simulate the human infection risk based on climate and adding movement to all of the models to complete the trio of components that create effective models, so that all parts of the project can be encompassed. And the title, Building Computational Models to Understand the Interplay Between Climatic Factors, Air, Transportation, and Infectious Disease Dynamics, is complete. And that is all I have. Thank you.
We have time for one question.
Where do you get your guys' animal or bird, I think it was, abundance data from?
I can't remember where that data was from. It was... Kyrie, do you remember where that data was from?
Yeah, the data is from the Department of Health Services in Maricopa County. So,
All right, thank you. Yep. Okay. Our next speaker is also from Northern Arizona University, Cameron.
okay.
Some laser pointers,
So I use this up here.
Hang on a second. This is PowerPoint. I need to put it into the slide.
Oh, this is that means there's
Right on this, right?
Alright, how's it going, everybody? My name is Cameron. So this is my presentation. My professor is Dr. Christopher Doherty and Dr. Michael Gowanlock. So my presentation is on the habitability and potential for life on a planet called TRAPPIST-1e, and I'm from NDU. So just to start off, so like what is the TRAPPIST-1 system? So essentially it's just a planetary system, essentially like a series of planets to have a red dwarf star being like their equivalent of a sun, TRAPPIST-1b, C, D, E, F, and G. So essentially what I and me and my professors are doing is like analyzing the potential for life on this planet specifically because it lies in like the Goldilocks zone. So the Goldilocks zone is just like the perfect distance from that star, and it's like the most Earth-like planet that we know of today. So it's like it's enough heat to the point where it can support life, and then not enough heat or not too much heat to the point where it would just exterminate all life. So we analyzed this, and this is like the statistics regarding the Earth-like abundance of this planet. So we have like their Earth equivalent of a year is 6 days. So it rotates their sun in 6 days. Here, the radius is very similar to Earth. Mass is relatively similar. Density is pretty much the same, and a very similar gravitational pull. So by analyzing all these, we're like realizing that it is very Earth-like similar, and then we can essentially model if life would exist on this planet. Just specifically like photosynthetic life, of utilizing those rays. So what we do is essentially like estimate the photosynthetic potential on this planet through a process called like net primary production. So what is net primary production? So net primary production is essentially like how much energy is a plant using for its own metabolic processes that it can then contribute towards future growth. So like how much energy can I have in excess to then contribute to new growth, new plant life, etc. So due to the fact that this planet is so far away, we can only like estimate very simple parameters. It's 41 light years away, so we'll most likely never get to it in our lifetime, very likely. So we utilize just light, temperature, precipitation, the three things we all know contribute towards photosynthesis. So we kept it simple because of those only parameters that we can essentially utilize. So then we estimated, like, can we predict like the evolutionary stage of this planet and compare it to Earth because it is the most Earth-like planet. And this is just a general estimation as to like the components of the planet. We don't know. Maybe there's clouds, maybe there's not. Maybe there's water, maybe there's not. We're not sure. So what we did was just compare it with like an evolutionary timeline of TRAPPIST versus Earth. So we have simple cellular life versus multicellular life. We just kind of just like general estimate to put things in perspective. We have like the orientation, the origin of Earth. This is when simple cellular life emerged, and then multicellular life from plants, animals, etc. So if we estimated that the same thing as TRAPPIST-1e, we have simple cellular life, multicellular life. So it's like, are they evolutionarily ahead of us or behind us is like the main question we're trying to answer. So what we did is essentially put all this data into our model that we created. Again, we use our simple parameters, precipitation, light, temperature. So these are just different infographics and different visuals of those outputs. So we have temperature, precipitation, light, and NPP, or net primary production. So here we have and it's important to mention that TRAPPIST-1 is a tidally locked planet, meaning only one side of the planet is always exposed to sunlight. So as it's rotating, it's rotating very slowly, but it's only exposing one side of the planet to sunlight. So in that sense, light is only on the one side of the planet. Life can only exist on that side of the planet as we're estimating. Here's temperature, precipitation, and this is all compared to Earth, which we know the data of very easily. And you see in this that there's a slight little deviation from light exposure that can be an estimation of clouds and precipitation. And at the bottom we have net primary production. So that's just a better visualization of everything. So Here's our photosynthetic life model outputs. So we compare it with like different analysis data, different data inputs regarding like low light conditions, very wet conditions, and how that would affect like carbon fixed. So essentially, like, what is carbon fixed? Carbon fixed is just utilizing like atmospheric carbon dioxide for the purpose of photosynthetic, metabolism and life. So how much carbon dioxide is being fixed in the purpose of photosynthesis? So we plot these on this graph, and we estimate under different conditions, what is TRAPPIST-1e most likely like, and this is our general estimation. And we compare this all with Earth being the black line, and here's our current day. So then again, we also ask the question, is it evolutionary ahead of us or behind us? We don't know, but that's what we're trying to estimate and predict. So then we essentially estimate like an Earth similarity index. How does a lot of these planets that we find out compare to that to Earth? So like, sometimes they get a bit clustered, but we're analyzing carbon fixed versus the Earth similarity index to plot where does our planet lie in comparison to everything else. You see there's some pretty big deviations, K2-3D, some of the planet, another planetary system, but here we have TRAPPIST-1e. And the other planets in TRAPPIST, the planetary system. So this just visualizes everything with regards to where it is in regards to Earth and carbon fixed. So, what does the future of planetary science look like? So we're essentially waiting for a telescope called the James Webb Space Telescope. It was a multi-billion-dollar project funded by NASA that analyzes spectral analysis of different planets, essentially just looking for the output and input of wavelengths of light, and that is then used to estimate what does this planet look like, what does the atmosphere look like, can we then understand the geography, the composition of the planet, and the potential for life on that planet. And here's TRAPPIST-1, so this is the red dwarf star. Compare that to our Earth, or our Earth-Sun relationship. This is theirs, so it's a very small planet. It's around the size of Saturn, or a small star, and they're very common without the universe. So this is 41 light years, like I said. It just puts things in perspective, and it's very cool. So the distance between that and the planet TRAPPIST-1e is very important for the purpose of photosynthesis and facilitating life. So, and that's it. Any questions or comments? Yes.
So M-type stars tend to be pretty energetic.
Mm-hmm.
Did you take that into account as far as the radiation?
Yes, we did, because there can be fluxes in solar radiation, and we understand that the wavelength of light is also very different. We kind of just estimate that if life would exist, they would have to utilize wavelengths greater than 700 nanometers for the purpose of microbial life or photosynthetic life. So we did take that into consideration. Yes.
What does the atmosphere look like on this planet?
So the atmosphere is really hard to estimate because there's essentially existing a Hubble telescope, analysis of the Earth of the planet's composition. So we're waiting for the James Webb Space Telescope for that Earth composition of the planet analysis. Because currently we don't know all that much, so we're waiting for more data, and that should be upcoming because it is in circulation right now within the universe. Yeah. What's up?
So you said only the sun faces one side of the planet. Does that mean the other side of the planet is just completely frozen?
Yeah, it's completely dark all the time, so there's no sunlight. So yes, most likely it is probably frozen because there is no sun exposure. Cool.
All right, let's thank Cameron. I should mention briefly that the session is being recorded. If you don't want it to be recorded, speak to the gentleman in the back here. And further information about the recordings. So next up, we have Emily, also from Northern Arizona University. All right, thank you.
Hello everyone, my name is Emily Clark. I'm from Northern Arizona University, and my project is entitled Space Weathering of Dark Regolith and Carbonaceous Asteroids, and this was done under the mentorship of Dr. Mark Ledley. So a little bit of background. So what exactly is space weathering? Most of us know that things on Earth get weathered through atmospheric processes, but for bodies without atmospheres, such as asteroids, dwarf planets, and moons, they get weathered in different ways. So they don't have atmospheres, so they're exposed to the conditions of space. So they're exposed to micrometeorite bombardment, cosmic rays, and solar wind. Something important to note is that magnetite is a very important component in these carbonaceous asteroid surfaces, especially in Bennu, which is the subject of NASA's OSIRIS-REx mission, which we're all excited about. And it's really important that we do lab experiments here on Earth to help us understand the spectra of these materials, so that when we compare this data to remote sensing observations, we can see if space weathering has occurred. So the inspiration for this study was a paper, Chavez 2023, and what they did is they irradiated magnetite with protons. And they found that there's this really drastic spectral bluing in the 0.7 to 1 micron region, and also an increase in brightness. They also were able to look at the surface and observe that it was chemically reduced to iron, which was really interesting because iron's usually associated with spectral reddening and not bluing. So we kind of wanted to look into this more and wanted to investigate space weathering of magnetite and other dark materials in more detail. So we chose to do studies on both magnetite and CI simulant because they're both important components of asteroids. So to do this, I prepared pressed samples of both the magnetite and CI simulant. And then before I did anything, I characterized the initial reflectance spectra in the ultraviolet visible and near infrared ranges. And then I put these samples into our ultra-high vacuum system, which gets down to pressures of about 10 to the -8 torr. And so this is a picture of kind of that setup. Right here is that ultra-high vacuum system, and we have two spectrometers that point into the system, but we use different ones outside of the system. And then we also have a laser that reflects onto this rastering mirror and back into the system. This is a schematic of that same system I just showed. So we can see that the laser goes into the chamber and hits this target. And so on that target, there's a piece of metallic iron. And as the laser hits it, material gets blown off and it's collected onto this catcher plate, which is where I put my samples. And so this material getting blown onto the sample kind of simulates when there's a micrometeorite impact, and then material gets blown off of the surface and then subsequently redeposits back onto the surface. So I did this, ablated the iron with the laser, and then I removed the samples at pre-specified intervals of different thin film iron deposits to perform reflectance spectroscopy, and those intervals are listed right here. So some results for magnetite. Here I have plotted the absolute reflectance versus wavelength, and then each curve is a different thickness of iron, and so you can see it kind of on the side here. So what we notice is that the reflectance increases with more iron at all wavelengths, which is expected and makes sense because iron's a reflective material. What we did observe is a slight bluing between the fresh and 20 nanometers in this 0.7 to 1 micron range right here. But it was very slight, and it was not nearly as drastic as what the Chavez 2023 study found. And then I took the average slopes across the UV vis and near IR regions. And so this blue line is the UV vis, and the red is the near IR. And so we can see that the UV vis, it starts out kind of blue, and then it gets more red as we add iron. And then in the IR, it just pretty much reddens the whole time. So I performed the same analysis for the CI simulant, and something interesting is that the reflectance initially decreased, actually. So this black curve is the fresh, and then the red is 5 nanometers. So it initially decreased, but then it subsequently increased after that. Another thing we noticed is that this absorption band around 0.8 microns gets attenuated, and so as we add more iron, the spectra kind of begins to mimic iron more so than the CI simulant. And overall, we noticed similar trends that the magnetite showed, which suggests that these materials space weather in similar ways. And I did the average slopes again for the CI simulant. We see that in the UV vis, this has this really steep bluing at the beginning, but we pretty much attribute that to just that attenuation of the absorption band. like I mentioned before, and then in the IR it just pretty steadily reddens. So some conclusions is that depositing metallic iron onto dark materials overall causes an increase in reflectance, and the spectral slope overall reddens with more iron. This is consistent with studies done on brighter silicates. And while we did find that spectral bluing that we were looking for in the 0.7 to 1 micron range for magnetite, it was very slight and it's not as drastic as what was shown for proton irradiation. This suggests that this might be part of the explanation to what they were observing, but it's definitely not the entire picture. So future work, I will be repeating this procedure with a brighter material, and we chose olivine because it's also an important component of asteroids. Here's a picture of a meteor, and all these green bunches right here are olivine embedded in the meteor. So we can clearly see that it's important. And ultimately, we hope that this data can be used to compare to remote sensing observations. And this is super important for analyzing the samples that we just got back from OSIRIS-REx, which I'm super excited about. That's it, thank you.
We have time for questions.
Hi, I have a question about the experimental setup. In the slide you show that there is kind of a lens that is focusing the laser. How important is this focusing? Because sometimes laser can be fairly small in diameter.
Yeah, so our laser is pretty small in diameter, but so is the metal sheet and our sample. And so while the light, it does get focused, but it's like very precise and controlled by like millimeter movements.
The CI simulant, is it a simulant for the general mineralogy of a carbonaceous asteroid?
Yeah.
Okay.
Yeah.
Just wondering, when you're bombarding it with radiation like that, is it causing any color centers or anything like that? Like just look at electrons and things like that? Like certain mineral, when you hit it with radiation, it changes color because they got different, maybe an atom got knocked out or maybe an electron came out, I don't know.
Yeah, so we haven't necessarily observed that, but we still plan in our future work to like put these under an SEM and observe the surface and see if something like that might have occurred. But since we're not directly hitting it with the laser and just depositing iron, we don't expect it to be as harsh of an impact.
Do you have time for any more questions?
I thought it was really interesting that it only took 20 nanometers to completely erase the spectrum in the CI simulant to get rid of that band at whatever it was, 1.5 microns.
Yeah, I found that interesting too because it suggests that we don't need too much of that redeposition to kind of cover up the main surface components.
Yeah. So when you look at space weathering in natural materials, is it mostly metallic iron or iron? Well, it's kind of a mixture. Do you get metallic iron particles, or do you get iron oxide particles?
That's a good question. Most lab studies use like nanophase iron particles, and so I'm sure iron oxide is like a good possibility, but we mostly just look at iron.
Okay.
All right. Let's thank you again. Our next speaker is also from Northern Arizona University, representing here today, Jessica. Hello, my name is Jessica Maldonado, and I'm also from Northern Arizona University, and this is my project on the optimization of linear map distortion. And so a bit about what this presentation is going to go on. It's going to go into a bit about what map projections are, map projection distortions, so methods I use to minimize distortion, my results and conclusions. And this project was a comparison technique. And so it was comparing map projections under two refinement techniques, one being a manual implementation of what's done today, and an optimization algorithm
that we're testing that could potentially be done. And so what are map projections? Map projections are a method for representing a part of a planetary surface on a plane. And I looked at 3 specific map projections. I looked at the stereographic projection, which is a planar projection. I also looked at the transverse Mercator, which is a cylindrical projection. And finally, I looked at the lambda conic conformal, which is a conic projection. And then you can see the types of projections on the figures to the right. And so, essentially the sphere in the middle, in my case, would represent the moon. And the geometric shape that's wrapping around the spheroid would represent the map. And the map is projected onto the surface of the geometric shape. And so the reason why different map projections are used is that they balance distortion based on what aspects of the spheroid surface they prioritize. So some may prioritize areas, angles, or distances. And so a problem is when you take a 3D object and flatten it on a 2D sphere, distortion occurs from flattening, elevation, and curvature. And so specifically looking at this figure right here, this would represent our map, and this would represent our actual ground distance. And so you can see how flattening something like that can cause distortion. And so this means that the distances on the map may not be entirely accurate. And looking at these 2 figures right here, these are 2 systems used to project locations on the Earth's surface. And so each system has its own use. This is the UTM, mostly used for navigation. And then this is the one I focused on, which is the state plate coordinate system. And this system is used to minimize distortion because it splits the map into smaller zones. And so some methods I used, the first one was the manual method, and it's the one that is currently being used today. And so the whole point was to calculate the combined scale factor, which we get from calculating first the elevation factor and the grid scale factor. And when we take the product of these 2, you get the combined scale factor, which is used to correct combined linear distortion. And so that's the method that's currently being used. What we are testing was an optimization method, which is I took from a SciPy library, and it's called the dual annealing algorithm. And so this just takes an initial solution, and it iteratively looks for the best solution. And the main goal for this one was to get the residual to be as close as 1 as it could possibly be. And this just means that it's as close to true scale as possible, and no distortion is there. And so this is the area that we were looking at. This is the south pole of the moon, and I was specifically looking at the Noble Rim area. And as you can see, the moon is a super mountainous area with deep craters and peaks. And so you can see how flattening on the map can cause distortion. And so again, the main goal was to scale the map so it could represent the ground more accurately and minimize distortion so it can be as close to ground distance as it can possibly be. And so, discussing the techniques I used earlier, I was able to come up with these plots under stereographic projection with the manual technique and the optimized technique. And I want to kind of highlight the scale bar right here. And so you can see the lowest combined factor for the manual implementation was about 0.994, which when converted to meters, it's about negative 0.5 meters per kilometer, which means it's negative value, so it represents a more shrunken and compressed scale, where 1 unit of the plot corresponds to a fraction of a meter in reality. The same case for the optimized version. If you look at the scale, it corresponds to negative 0.5 meters per kilometer, all the way to negative 0.5 meters per kilometer. So both of these plots are more shrunken than how they are in actual distance, so they don't quite reach where they're supposed to, but they're just a little bit off. And then I did the same with the transverse Mercator, where the manual implementation was about negative 0.4 meters off per kilometer. And then the optimized version was actually 1.5 meters per kilometer, which means instead of it being shrunken, it was more enlarged. So it actually passes the point instead of not really reaching it. And then the final one I looked at was the lambda conic conformal. This one was a little bit more complicated, and so the plots are a little bit more off than both the transverse Mercator and the stereographic because it takes in more parameters. instead of just taking a projection axis or a projection point, it takes in 2 standard parallels plus a bit more. So this one is still a little bit of a work in progress. But you can see here on the table, these are the results I came up with. And so for each given projection, I moved around the initial point. And from there, the results still seem to be a little bit inconclusive because this project is still a work in progress. But I did come up with some trade-offs between the manual implementation and the optimized algorithm. And the first one being time. The optimized algorithm went through thousands of potential optimized versions, and so each run took about 40 minutes on my computer. So if working on a project and using this, if time is a little bit scarce, maybe using the optimization algorithm isn't your best choice. But complexity did work a lot better. Like I said, the lambda chronicle formula took in about 5 parameters, and so hard coding each one, each time you ran it for the manual implementation, was a bit redundant. So using the optimized algorithm was a little bit better. And some future work to explore the feasibility of other map projections and prove minimization through data visualization and research and optimization. So that's my project. Thank you.
Plenty of time for questions. I know there are map projection nerds in this audience, besides me.
As a map projection nerd, because you're working all in digitized maps, the 2 map projections that you were using were made to roll up a map and store it in a scroll rack. Have you messed with any map projections like a good projection that would, GOD, not good, that would work in a really non-traditional shape, but that might turn out perfectly on a computer screen?
No, so I only worked on the 3 map projections I said here, but this is an ongoing project and we were planning to work on other map projections further along the line.
Yeah, and I guess my question is, are you going to work on any that are non-square in your future work? Have you worked on any that don't produce a square projection or rectangular projection?
No, I don't think so. Not yet.
You might find higher levels of accuracy with some GODE, a good projection, cuts it like an orange. So they're these weird cylinder shapes that go back and forth, and they'll maybe address these issues. It's just something to look into.
So I have a question about your lunar study. Is there a particular motivation for the study of the south pole of the moon?
Yeah, so like I mentioned, we were mainly looking at the Artemis landing sites. So just for navigation purposes, to see if we can find a method that might be easier for navigation. But we were just looking into testing the optimization one to see if it would work better than the manual one.
Okay. So you're taking the lunar maps and then providing to the astronauts something that has more accuracy as far as like reading the map to where they are on the surface.
Yeah, potentially.
Maybe. Any other questions?
Give a little more time.
Yeah. Well, thank you, Jessica. Really interesting. So next up we have Letitia. I hope I pronounced that correctly. Did I mispronounce it? Sorry, you're not. Yes. Yes. Okay. Yes. Letitia is from Arizona State University.
We're a little ahead of time, so let's let people call in before we start. Come on in. That's awesome.
Okay. Yeah.
All right, let's give Letitia our attention.
Thank you. Good morning, everyone. My name is Ritisha Das, and I am a senior at Arizona State University, researching with Dr. Ming Li on investigating the cause of Mars' large volcanoes from deep mantle convection. So my project rests on the premise of mantle plumes, so to start by explaining what plumes are. Mantle plumes are hot, buoyant rock that rise from deep within the planet up to the next intermediate layer, the mantle, up to beneath the crust. And it can give way to phenomena such as volcanoes, quakes, and faulting. And specifically, current literature and research indicates that if you analyze the thermal boundary layer of Mars, the instability will show that there's only one superplume on Mars, which gives way to the largest volcano in not only Mars, but in the solar system. If we can analyze why this plume exists and what conditions causes the creation of this mantle plume, we would better be able to understand the topographical differences in the northern and southern hemisphere of Mars, as can be seen in that topographical figure at the top. This is known as crustal dichotomy, where 40% of Mars's terrain is in low elevation and 60% of Mars's terrain in the southern hemisphere is in high elevation. And so we hope to understand in this project specifically what kind of parameters we can apply in a simulated environment to recreate this single superplume phenomenon on Mars. And it's also affected by this phenomena called Rayleigh-Taylor instability, as indicated in this sort of figure, which is just a fancy way of explaining what the interaction is between a heavy fluid and a light fluid. The heavy fluid pushes on that light fluid in the mantle and causes the light fluid to sort of move up and create this plume-like formation as we see right here. And so these are some byproducts of what researching this question would sort of yield in terms of insight. We would better be able to understand the realism and the possibility of life on Mars, the planetary evolution of Mars, parallels with sort of evolution of Earth, seismologically and topographically, and more seismological information about Mars. And so, again, my specific question in sort of the context of all this is what can I do in a simulated numerical environment to recreate this single plume formation? A lot of the problem is that we know how a lot of these factors sort of trend, but we have not been able to achieve the recreation of just a single mantle plume when we apply certain initial conditions to a Mars simulation, and so that's kind of the focus of this project. I'm utilizing computer simulations in SITCOM-S and analyzing observational data available to me through the Geophysical Insight mission. SITCOM-S is just a finite element code that can solve compressible thermochemical convection problems about a planet's mantle. Fancy way of just saying that we're able to sort of analyze the heat transfer capabilities of spherical objects by solving the conservation of mass, energy, and momentum. And what's interesting about this is that I can apply this to a rubber ball. I can also apply it to a planet data. It really is just sort of analyzing the heat transfer. And so this is the methodology that I utilize to sort of answer that question. I first used Linux coding to execute different simulations in SITCOM-S in sort of a readable format for a user over a time period from 0 to 50,000 time steps. And then I had to apply a bunch of initial conditions, so we picked 2 specific parameters to analyze and see how that impacted the mantle plume formation in our figures. And so I varied the Rayleigh numbers, which has to do with that instability we were talking about a little earlier, between 1.25 times 10 to the 7th and 1.25 times 10 to the 9th. And the internal heating rates were supposed to be varied between 50 and 200 in increments of 25. Then I wanted to record all the mantle temperatures at fixed depths at longitudinal and latitudinal data and aggregate that coordinate data to create 2D heat maps in a MATLAB algorithm that I designed over the last year. Then the idea is to repeat this entire process iteratively to adjust the initial condition parameters and see how those are affecting my figures, and then sort of like make adjustments in those initial conditions to make figures that are more closely realistic. And then you would repeat the MATLAB plotting, data aggregation to visualize and track the patterns. This is sort of a pictorial representation of what I just described. SITCOM-S sort of looks at spherical objects in slices, and so there are 48 processors that comprise Mars in slices, storing values of sort of radius, theta, and phi, which is just depth, longitude, and latitude. And then we record the temperatures from a non-dimensional number from 0 to 1 for easy reading and just simplification of processing of data for all those initial conditions that we applied. And then we download the data at a specific time step, because remember, we're doing all this for multiple time steps, so the data is very large. And so to make it readable, we want to just isolate for a specific time step. And then in my MATLAB algorithm, we pick a specific depth. We aggregate the longitude and latitude again to the heat map, as you can see here, and then repeat the whole process. And so here is sort of some of the results that we've got. I will add that majority of my year was kind of spent on creating the algorithm that could read that data, so the results were a little difficult to sort of get within that timeline as well. But what we were able to see is that this is a figure that was created through a MATLAB algorithm. And so for a specific Rayleigh number of 1.25 × 10⁷, at an early time step, we see a bunch of sort of patches. The yellow is actually higher temperatures versus the blue being lower temperatures. And these are actually, this shows that we have not actually seen the impact of the Rayleigh number because the time step is too early. This is a temperature gradient that we sort of impose on Mars's mantle as a result of a Rayleigh number. And then over that time, all the way through 50,000 time steps, you see sort of an impact. But here, we're not seeing the impact. We're seeing the initial condition. So that's how we knew we needed to sort of evolve and pick a later time step when we downloaded our data to process. Then here we have our simulations we address that problem sort of, and we saw for a specific Rayleigh number what it would look like from 3 different time steps. And so as the time moves on, these red patches are the mantle plumes because they are of a higher temperature between the numbers of 0 and 1. And as time moves on, you see the mantle plumes get more defined. So this is how many mantle plumes we're seeing as a result of this number. And then at the very end, for the 45,000 time step, because it's 5,000, 10,000, 45,000 time step, we sort of reach a thermal equilibrium at a higher mantle temperature. And then these are isosurface models. So we're doing those maps to also see the impact of internal heating rate, but we also wanted to show you guys sort of what the 3D structure looks like. So instead of fixing the radius and plotting temperature, we fixed the temperature and we plotted all the coordinate data for the internal heating rate of 50 versus 75. And as you can see, these are all mantle plume structures, and there isn't a significant difference that can be really seen. And so this kind of indicated that we needed to plot more simulations for internal heating rate. So sort of recapping what we were talking about, while not included in this presentation, there were a lot of 2D heat maps that we were able to create between the time of the presentation being submitted and today. And so that actually revealed that higher Rayleigh numbers correlate with a higher number of mantle plumes, so we want to trend lower. And that matches sort of the theory that we're looking for, because higher Rayleigh numbers increases the convection rate. And there's an unclear relationship between internal heating rate and number of mantle plumes and Rayleigh numbers. And so theoretically, what we are expecting is higher internal heating rate lowers viscosity, creating smaller plume sizes in space for more mantle plumes to form. So next step, more simulations for internal heating rates and creating code to process those MATLAB graphs. You saw like the blue and yellow, there were some gaps in the side that we want smoothed. Thank you to my mentor, Dr. Lee, and to everyone else at ASU that gave me this opportunity.
So you're saying that in your simulation the higher Rayleigh number correlates with the number of plumes. So are you using spherical symmetric initial condition, and if so, is it possible that if you break the spherical symmetry in the initial condition, that is going to have a role too in the number of plumes?
Yes, so the data actually comes in spherical coordinate form from sitcom-S, and so we didn't have to impose another parameter to read it as, but in my creation of the algorithm, I did notice that if I strayed from spherical, I was getting a higher number of mantle plumes because the data seemed to be mismatched and not sort of in the right locations, and so the mantle plume sort of temperature data were sort of scattered. So it does need to be in a spherical sort of coordinate system to be able to see it in the way that it's most accurate. I hope that answers your question.
We can take it offline.
Yeah.
Any other questions? I have a question for you. Do you have a next direction for this research?
Yeah.
It's a very interesting result.
Yeah, I'm hoping to just create a greater number of simulations. A lot of the time this year is spent on aggregating the data and making it readable for me. So I think now it's going to be trying to figure out the optimal combination between internal heating rate and Rayleigh number and how that will impact the number of plumes. Because as you can see in the graphs, we have way too many plumes.
I have a question. So, what's the reason for one superplume on Mars? Or what do people think is the reason for one superplume?
There's a lot of speculation, and at least for literature-wise, like all I was able to really find is that everyone's saying that it has to do with the volcano existing on Mars. I really can't give you a greater explanation. I hope to find out more in my research in the future.
All right, let's thank you again. Okay, now we have two presenters from Embry-Riddle Aeronautical University, Nathan and Winona.
Is it possible to dim the lights at all?
I don't know how, but we'll try. Let me give this to you. Perfect. Picture
And then put it in this, we all see it yet, but then put it in the slide.
Yeah, you can
It's important though that you start the process before the 10 minutes is up. About 9 minutes, whether you're
So I'll change the stage and you introduce the people.
Absolutely. Yep. So for those of you that are just coming in now, this is now session E, Exploration Systems, Engineering, Biological, Materials, Optical, and Electrical. We'll be running through these fairly quick. They're 10 minutes. So that means is that when you get down to 3 minutes, I'll hold the sign. When you get down to 1 minute, I'll hold the sign. If we get down and out of your time, you'll have a lovely round of applause starting from me, and then we will continue to take questions afterward. Our first presenters here are Nathan and Winona, Mineral Aeronautical University. Thank you.
Thank you. Hello everyone, welcome and good afternoon. My name is Winona.
My name is Nathan Blakely.
We are both undergraduate researchers at Embry-Riddle Aeronautical University, focusing on investigation of stress concentrations within fused deposition modeled parts, and we will be getting into our presentation. I would first like to acknowledge my mentor, Dr. Lanning, as well as Dr. Betcher and Dr. Briner, who have assisted us throughout the entirety of this URI project, as well as Embry-Riddle for allowing us to continue all of our research and funding and help us through the undergraduate research institute that we have on campus, as well as Spacegrant for hosting everyone today. First, a general introduction of what fused deposition modeling is. It is when you take a thermoplastic filament layer and you then extrude it in, heat it up to its melting temperature, and then deposit it through a nozzle layer by layer onto the actual plate and platform, where it then is able to manufacture and effectively create a fully developed and manufactured 3D printed part. Yes, fused deposition modeling is basically 3D printing, or more commonly known as rapid prototyping within an industry. There are many different parameter variations that are included and can affect the mechanical properties and strengths within 3D printed parts and fused deposition modeling, many of which we have been able to consolidate and concise into the 4 labeled as such, which are our solid top layer, the parameters around, which are the effective shell areas. We are focusing specifically on gyroid infill patterns with densities of 20, 40, and 60%, as well as the solid bottom layer. The focusing on gyroids infill density at 20, 40, and 60 allows us to better compare all of our results with previously tested results of circular holes and semicircular holes, as shown in this slide. So, according to traditional solid mechanic theory, you can see that the highest stress concentration area is going to be here, 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 and here in our locations. So, there will be the highest stress at the reduced effective area within a 3D printed specimen. So, at those locations where there is the highest stress, we are going to see the high stress concentration factor, and that's where the predicted part is going to fail. Within our elliptical and V notches shown in the bottom 2 images, we're trying to induce a higher stress at those locations while keeping the same theoretical stress concentration factor to try to induce the stress propagation throughout those locations. We currently use a SATEC tensile testing machine on campus, which is basically a hydraulic testing machine, so it grips down on the bottom end of the specimen and will respectively grip the top end. And to prevent any of the crushing of the actual specimen, we have induced these high-density grip tabs on either side of our specimen, which are incorporated while we 3D print and manufacture all of our specimens. So it's basically creating a box of 90% infill at these locations, where the infill is actually going to be the 20-40% at the bottom ends and 90% on either side.
So, from prior results from our testing, we have found that failure locations will deviate from where we predicted, such as for this whole piece, we can see that no crack forms right here, but instead forms up here. This is where the stress is lowest in the part, so instead of failing here, it fails here. In some cases, when the crack is traveling through the part where we expected, sometimes it'll fracture off into 2 directions, causing the piece to splinter. And in some cases, a crack will begin at the point where stress is lowest and will travel to another point where stress is lowest.
So, for our nominal stress at failure, we have this graph. This, for the y-axis, we display the nominal stress. The nominal stress is calculated from the maximum load applied to a part divided by the reduced area of the part. The x-axis is our theoretical stress concentration factor, starting from 2.2 to 2.4 to 2.5. And for our bars, we have our notches, our holes, our V-notches, the ellipses, with our 20 to 40 to 60% infill densities. As you can see from our testing, the nominal stress decreases as our stress concentration increases. So next we are comparing our theoretical stress concentration factor to our experimentally derived stress concentration. So for the gray bar right here, we have our theoretical stress concentration. Our y-axis is our stress concentration, and our x is our diameter to width ratio. As you can see, our experimental stress concentration factor is much lower than our theoretical predicted values.
So the shell strength impacts a lot of our actual stress that we have been being able to test within our 3D printed part. The shell stress is able to be calculated by the maximum applied load divided by the respective shell area of the circle or notch locations. And so within this, we were able to determine that the shell has much more of an impact than we were originally predicting, where traditional theory would state that the failure is going to be located around this location. However, because of the reinforcements that the shell provides, we are seeing opposing beliefs and experiments within our results. So the results that we have seen from our elliptical and V-notch tests that we have run is that it looks pretty good from all of the sides. You can see it start to propagate through the actual highest stress concentration area that we were predicting to see. However, some interesting things happened when we were testing, so that it broke primarily first on this side and was still able to hold load on the right-hand side or the left-hand side of the specimen. Furthermore, with our V-notches, we were able to determine that through other testing types, we were able to determine that the crack propagation starts at the highest stress concentration, but then deviates towards the lowest predicted stress concentration area, which is not what you would assume to be happening. As well as we were having additional problems within our testing parameters, where the specimen would fail at the grip tab location. So instead of failing at like the middle point area, it would fail at the bottom area, where we noticed there was a small gap within our parameters when we were printing. So instead of actually having a smooth transition from the 90% infill density to the infill density that we were planning at, it would then be proceeded to go to a gap which induces more stress concentration at that location.
During some of our tensile testing, we were able to incorporate the use of a high-speed phantom camera where we recorded our pieces at 200,000 frames per second. As you can see, we are able to capture the beginning of a crack on one of our V-notch pieces as it's able to travel through our pieces. As you can see, the crack is not going to directly adjacent to the other side and instead going slightly downward. We believe that this is because it is following the internal infill geometry. During some of our high-speed testing on separate other pieces, we can see the crack is beginning and traveling through these pieces. However, on this third image right here, we see these strange cracks right here. We don't know exactly what these are, but we believe that this is some kind of delamination, or it is a crack traveling throughout the entire piece. But as soon as the entire fracture occurs, these delamination or cracks disappear.
So to wrap up what we have experienced within our testing as a whole, we have noticed that as we increase the infill density, that it's able to hold more load. That's basically, we're increasing the actual parameters of the specimen. There's more material that it's able to withstand the load. We also, as we increase the density, we're seeing that it becomes more homogeneous, so it's following traditional solid mechanic theory more than the densities of the specimens of lesser density. We have also determined that the traditional solid mechanic theory that we have been using is not applicable to the specimens that we have been testing in 3D printed parts, so further exploration needs to go into that as to what FEA models would be good for 3D printed parts as opposed to what's currently being used in industry, as well as the shell printing parameters affecting the specimen more than we were expecting, and possible viscoelastic properties within the 3D printed part itself, which was what Nathan was discussing, with the cracks being visible and then not visible in the next image. Are there any questions? Thank you.
We'll have to hold questions for the next one so we can have time for everybody to present, but we'll have questions after.
Yes, please ask.
Our next presenter is Chad Panton from the University of Arizona.
Hi everyone, so my name is Chad, and today I'm going to be talking about the NASA Surveyor program, more specifically Surveyors 1, 3, 5, 6, and 7, which were each of the spacecrafts. So some background, NASA Surveyor program landed 5 spacecraft on the lunar surface in the late 1960s, basically in preparation for the Apollo missions, and on these missions they captured thousands of images, 87,000, give or take. And all these images were, taken on physical film rolls and later transferred to 70mm film rolls. So this project ultimately aims to digitize all these pictures and kind of archive them so they can be publicly available to everyone instead of just stored in the Imagery Center at the University of Arizona. Just for some background, I'll be saying metadata a lot. That's basically the data that's to the side of the image you'll see on the next slide. That's just a lot of the background information on the photo. Some overall objectives for the project, pretty straightforward, digitize the image metadata. A lot of this is done in Microsoft Excel and was already previously completed, so a lot of my work has focused on kind of quality checking all of this data within Microsoft Excel or Google Sheets, and kind of just correcting inaccurate metadata. And then ultimately we will send the finished spreadsheets to NASA for NASA's Planetary data system to publicly publish. And that figure is of one of the Surveyor spacecraft, Surveyor 3 it looks like, and pretty large for size. You can see it later. So here's one of the sample images. This is going to be the lunar surface. I know it's kind of tilted on its side. A lot of the pictures aren't oriented correctly. This is space. It's kind of confusing because you'll expect space, to be black and the lunar surface to be gray, but images were all taken in black and white. Obviously, they weren't returning color. And here's some of the metadata that I was talking about earlier. So all of this data is basically what we put on Microsoft Excel. So we include, the daytime group, which is this number up here, which is exactly what it sounds like. The day the photo was taken relative to, the day throughout the year, so day 264, and then time group, just, the time in hours and seconds that the photo was taken on. You have the elevation angle, the azimuth that the photo was taken at, and then just a bunch of other data, calibration, all the other important stuff that, cameras normally capture. So, methodology for the project. Like I said, organize the metadata within Microsoft Excel. A lot of this is obviously fairly simple. You just have to have really good attention to detail because you'll see in the next couple slides how small some of these errors can come up. As well as utilize scripts to kind of recognize the apparent metadata inaccuracies. This could include writing a script that recognizes a number where a letter should be listed or vice versa to kind of pull out the very obvious inaccuracies throughout the metadata. An example is, some of these photos just don't have any data listed. For some reason, it didn't get copied down. Again, this was in the late 60s, so there's a lot of issues that, randomly came up. But a lot of the pictures still pretty cool. A lot of them are overexposed or underexposed, so they don't turn out perfect. But there's a lot that are missing data, so those ones, we have to kind of filter out into their own tab. So here's an example from the Excel spreadsheet. I could not include the entire Excel spreadsheet because these span all the way to, past column Z in Excel. And I know I only included, up to here, but there's probably around 12,000 lines in Excel. So as you can see, if this 4 is listed as an A, it's kind of hard to notice. So that's why we kind of use scripts to recognize, this line, it looks like there's something wrong in it, so my job would be to go in and figure out what's wrong with that line. open up the actual physical image that we have on like a 4 terabyte hard drive because there's 80,000 pictures on it. And then figure out, oh, you know, this 4 was listed as an A. Corrected to a 4. So obviously it's a simple process, but it does take a lot of efforts to recognize where the accuracies are. So here's some of the columns, you know, image ID, that's like the actual ID that I would have on the hard drive. Daytime group, like I talked about, camera azimuth and elevation, and then the azimuth and elevation relative to the lunar surface. There's a lot of other unlisted things, like I said, you know, the camera resolution, the focus, the focal length, field of view, filter position, just etc. A lot of different parameters that, you know, I did not include. I figured everyone would love to see some of these pictures since they're not really publicly available, so here's some of these cool photos. A lot of them, like I said, can be overexposed, or they're not as exciting as these ones, but I included some that I thought were pretty cool because, you know, these are pretty clear. You can see the surface really well and space, and this one, I think it's from Surveyor 7, was pointed at the Earth. So these are some of the first pictures from the lunar surface that we actually got of Earth. And you can imagine how excited I was just coming across this picture and going, oh my god, I did not realize that we came across that. Here's the shadow of the spacecraft. That's also pretty cool. Another shadow. So overall results, we've basically corrected thousands of inaccuracies. It has taken quite some time, but there have been thousands of mistakes throughout these spreadsheets that have been corrected and fixed, and we're getting very close to finishing it. These spreadsheets for Surveyor 1, 3, and 5 over 75% completed. Surveyor 6 and 7 spreadsheets are over 90% completed with basically no errors left to correct. So some interpretations of these results. We have improved lunar surface data, as there's not a lot of data from the actual lunar surface. We haven't been to the moon since these missions, really. This also kind of encourages some more geospatial mapping on the lunar surface, and overall just historical preservation and public accessibility, so everyone who wants to do research on these images can do research on them. Some conclusions. Final efforts include comparing the physical image count to the spreadsheet line count, which is kind of what my work is focused on the past few weeks, just basically ensuring that we have an image for every line in our spreadsheet, because, you know, if we're missing an image but we have the data, then we need to figure out where the image went. And then, yeah, overall, verified image data will support lunar research and exploration in the coming years with the Artemis program. And you could also create some cool panoramic pictures if you combine a bunch of the 70mm squares correctly and get a whole view of the surface. Some acknowledgements. My mentor, Dr. Shane Byrne, for accepting me in this project, and I'd also like to acknowledge Justin Reynolson, who is now 97 years old. He worked on the original Surveyor spacecraft at NASA, and he is still putting forward effort every other week, meeting with Dr. Byrne and I. He's so passionate about finishing this, so we're really happy that we're almost done with it. And final acknowledgements to the NASA Space Grant and University of Arizona. Thank you.
A few questions.
So just a question about like your process. You mentioned when you showed that view of Earth, you know, you were kind of surprised to see that come up. Is any other interesting little rabbit holes that you kind of stumbled upon that maybe you could share with us?
There's a lot of pictures. Like I said, some of them are just like, it'll be like a black image, and it's nothing that exciting, but some of them are really, really clear, where you could see a lot of giant boulders that were right next to the spacecraft. And when I first started doing the research, I didn't really realize, you know, what area the spacecraft landed in, so I talked to Dr. Byrne. I was like, I didn't realize it landed right next to some giant boulders. Like, that could have easily damaged the spacecraft, or, you know, stuff like that. So there's not a ton of interesting stuff. There's some pretty cool pictures of the Earth. A lot of them look like the one that you saw. And then just a lot of the terrain, you know, you could kind of map out far in the distance, like, oh, there's like a crater right there, and stuff like that. So, anyway.
So your work basically had to do with metadata. You didn't really do any manipulation of the images, you just used those as
Correct, yeah. My work is mainly focused on the metadata that's already been copied into the spreadsheets. I'm not 100% sure when it was initially digitized. I know it was kind of
a long time ago at this point. So yeah, my work focuses on kind of opening the actual physical image and checking the metadata on it.
That's great work, great work. That card you showed, that was actually a negative, wasn't it? That's why space was brighter than...
Yeah.
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 Excellent, thank you very much. Next presenter will be Henry Garland from Northern Arizona University.
Okay, my name is Henry Garland, and I am a sophomore chemistry major at NAU, and I did a computational study of the electronic and optical properties of a transparent conductive oxide called indium tenoxide for applications in quantum optical devices. So a brief outline of this presentation is I will first introduce transparent conductive oxides and indium tenoxide, get into my methods, the work I contributed, finally interpret those results, and conclude. So transparent conductive oxides, or TCOs, are conductive materials with low absorption of visible light. They are typically in the form of thin films, and they have many applications such as in energy, like solar cells, display technologies like touchscreen displays, and also quantum optical devices such as superconducting single photon detectors, where the TCO will play a role in receiving light and receiving photons, and using those photons as information. So why indium tenoxide? Well, it's a very common and commercially available TCO semiconductor, but it has the unique ability to exhibit superconductivity at 2 to 4 Kelvin, which makes it a great candidate for quantum network and communication devices such as superconducting single photon detectors. However, it only superconducts at a certain charge carrier density. So the main charge carrier of choice for this project were sodium ions. And a nice side effect of this is that it increased the conductivity of our ITO thin films. However, it decreased the transparency of our ITO thin films. So a major theme of this work is trying to balance that fine line between transparency and conductivity. So the first bit of work I did for this project is I first made a Python script that automatically generates talk plots from large UV visible spectroscopy datasets. So you can see the talk plot far right over here, and they're unique because they have this region at the very end that linearizes out. And if you extrapolate a line from that linear region down to the x-axis, that intersection point will give you the optical band gap of your thin film material. And this is very useful for this kind of work because it tells you the minimum energy required of a photon for it to be absorbed by a material. So we want a material with a low absorption of visible light. We want a relatively high optical band gap so that the energy associated with a visible photon cannot be absorbed and is thus transparent. But there's a caveat to that, and it's that we're looking for a relative range because we want our ITO thin films to absorb UV light but not absorb visible light. So for that to occur, we need it to be in around a 3 to 4 EV range with some wiggle room. Absolute lowest we can go is 2.7 electron volts. So we can absorb UV light, but not visible light. And that has applications because if we have the transparent conductive oxide that absorbs UV light, it will protect the device from interference signals from UV light. The second bit of work I did for this project was to use density functional theory, or DFT, to predict the electronic and optical band gap of these ITO thin films. DFT is basically a long series of quantum mechanical calculations that gives you information about charge density and how electrons are moving and interacting within your system. To find the electronic band gap of my material, or my system, I had to first find the band diagram of ITO. And the band gap, the electronic band gap, is just the distance from this lower, very dense valence band to this upper, less dense conducting band, which for pure ITO with no sodium ions in it is around 1 electron volt. I had to get a bit creative for the optical band gap and simulate the electron energy loss spectrum for ITO. And I have to make a correction here because it is the energy associated with the first onset energy of peaks in the EO spectrum, and it is not 2.4 eV. When you zoom really far into data, you tend to see peaks that aren't really there. That was a mistake I made. It is very obviously at 4 eV, which makes sense. It would be an ITO film that absorbs UV, doesn't absorb visible light. So that's how I got those two parameters. So to interpret the results from DFT, we have this plot here right in the middle that shows an increasing optical band gap and a decreasing electronic band gap with increased sodium ion doping per ITO unit cell. So it shows a nice inverse relationship which lines up with experimental data. And if we wanted to find the most optimal sodium ion doping concentration, we're going to have to look at this intersection point right here.
This is because it's right at that cutoff at around 2.8 eV. It's also not at 0 eV electronic band gap, because we still want a semiconducting material. So that corresponds to around a 2.4 sodium ions per ITO unit cell being the most optimal sodium ion doping concentration. So to combine the theoretically found optical band gap to the experimentally found optical band gap from my talk plots, we have these two plots here where purple and blue corresponds to the theoretical optical band gap and then orange corresponds to the experimental. And as you can see, DFT would not be the greatest predictor of the optical band gap. And this is because the DFT calculations were done on an isolated ITO unit cell where bulk factors were not taken into account here, which have a heavy influence on the optical band gap, such as impurities, grain boundaries, and the polycrystalline structure of ITO affecting that optical band gap. However, what is similar is the first and most obvious one, is that as the sodium ion doping concentration increases, the optical band gap increases, thankfully. But a unique one is that if you look to the point specifically, not the line of best fit, for both plots, you can see that they increase in a stepwise fashion where they come in pairs. And so, thankfully, I use this as a basis of comparison when comparing theory to experimental data, and we have this bottom plot here where I matched those plateaus the best I could. And so if we were to take those 2.4 sodium ions we found earlier and use this graph where the bottom blue x-axis corresponds to sodium ions in a unit cell, to the top being sodium ion atom percent in an ITO solution, that would be this at around 4 electron volts, 3.5 to 4, sorry, not electron volts, sodium ion atom percent per ITO solution being the most optimal sodium ion doping concentration. And what's really cool about this is that experimentally we found the 3 sodium ion atom percent ITO solutions in thin films to perform the best in terms of balancing that transparency and that conductivity at the same time. But this data suggests that we can push that boundary a bit further to around 4 sodium ion atom percent. So in conclusion, DFT is a useful tool for electronic structure calculations. It can be sampled from that unit cell easily to the bulk material, but for the optical band gap it's much more difficult because of all the different factors that affect that optical properties in band gap. However, at low levels of theoretical doping, at about 0 to 4, we do see similarities in those plateaus and stepwise increase, which I could use to compare, and finally find the most optimal sodium ion doping concentration around 3.5 to 4 atom percent per ITO solution. I'd like to thank my laboratory partners, Madison King, Selena Lamborn, who's in the audience today. She will be going over the experimental portion of this project, and my amazing mentor, Dr. Stephanie Hurst. My funding source is CQN, Arizona NASA Space Grant, Gene Sherman Mini Grant, and the Monsoon High Performance Computer, NAU's supercomputer for allowing student use, and the ACU Iron Material Center for experimental measurements.
So it seems that your theoretical variation of the band gap is larger than the experimental one. Has anything to do with the impurities that kind of average out effects? Is there in the experimental case, you have more inhomogeneities in the crystal structure. So, do you have a theoretical explanation why your theoretical has larger variability than the experimental one?
My best guess would have to be ITO. I didn't include it in the slide, but ITO has this extreme polycrystalline structure, and I think due to both factors of ITO, that stacking and how light interacts within those stacking crystalline structures, it introduced the most variation. Sorry, this question's a bit difficult, right? Sorry, it's not a question I can answer.
Well, and the second thing, this is more than a question, is a comment.
Okay.
Half of your plot, the vertical bar, are not readable. So make sure when you give a presentation they are readable. If you go around, not this one, but there are a lot of the plots where the vertical fonts are very small.
Oh, okay.
So keep an eye on that.
Yeah, I just want to know how were you able to decide that this is the best fit? When you label this line of best fit, how were you able to decide that?
Yeah, I followed the behavior of the plotted points the best, and that's how I decided to use that line of best fit. Using a linear didn't get its behavior as accurate as third degree on the best fit.
You first use a linear
Say again?
regression? You use a linear regression first, or?
I do not know.
Okay.
Chi-square minimization. Okay, any more questions? Okay, I guess lunch is ready and it's waiting for everybody. I see. We will resume at 2 sharp.